All right. But the question that's rarely asked, what is it? Like, really? Like, we all experience it, but do we ever ask the question what it actually is? Well, I'm here to answer that. And unfortunately, it gets complicated. But let's just start out by saying light is a wave. Specifically, an electromagnetic wave. You see this little sine wave here? Hey, look, it's trigonometry. Um, that is an electric field, the E that's blue, and the magnetic field, B that's red. And as they move through the air, that is what light is. It's just a wave of electricity and magnetism. Um, Light's color comes from its wavelength, which is how far apart uh, the peaks are, or the valleys, whichever one you desire. We describe the wavelength with the letter lambda. Oh, baby, look at these undulations, you know it. Okay. And one interesting thing about light is that it can be polarized. So you know how the E vector here is going up and down? That means it's vertically polarized. If it were going left and right, that would mean it's horizontally polarized. And if it were spinning around, it would be circularly polarized. Actually, something interesting is that your computer screens do this. And if you own a pair of polarizing sunglasses, you can do a fun little experiment where you look at your computer screen through those sunglasses and then turn them sideways, and you'll watch as you suddenly are no longer able to see anything on the screen. So yeah, light is a wave, and we have proof it's a wave. Waves will often interfere with each other. Uh, And so when we have a system that creates two sources of light, let's say a double slit here, if it's a wave, when we shine a light at it, we'll be able to see what's known as an interference pattern, where we have this big bright spot in the middle, and then we have other spots that get dimmer and dimmer further away from the center. And when you do exactly that, that is what you see. This is exactly what an interference pattern looks like. And so, yeah, light's a wave. It's just a wave. That seems real simple. It behaves like a wave. It's a wave. But actually, it's a particle. Light specifically is a particle that is often emitted when an electron moves from a higher energy state to a lower energy state. You know how electrons orbit atoms? Well, though there are different levels at which they orbit. So the further away they are, the more energy they have. And so if they fall from the you can shine light on an atom to cause the electron to go from a lower level to a higher level, as shown here. Or you can cause the electron to go from a higher level to a lower level, which releases a photon. Each photon actually has a distinct, discrete energy. All of its energy comes in specific packets. Well, I know. Uh, And that energy is E times what's known as the Planck's constant h times the speed of light over lambda, the wavelength. And we can prove light isn't a wave, it's a particle. When we shine small amounts of light at a detector, we can literally see singular photons hit it. We don't see the kind of broad uh, distribution that we'd expect from a wave. We see it only appear in one point, so it can't be a wave. Because particles just don't act like that. Well, they don't. A wave would not present like this. That's like trying to sing a song and only one person in the audience hearing it. It would be a light meal? Yes, yes, it would. So, yeah, it's a particle. Ignore that wave nonsense. It's a particle. But wait, don't ignore that. If light is a particle, why does it do the wave thing when we did that double slit experiment before? If light was a particle, it'd be like you'd expect it to travel like throwing a baseball through those double slits. You're not going to throw a baseball this direction and then have most of them land in the middle. You'd just keep going. And same through this one. So why do we see this pattern here when, if we can but clearly see it's a particle, it should behave like this? So perhaps we can find out which slit the photon goes through. Maybe that will be the solution that we're looking for. Maybe that'll give us some clue as to why the photons suddenly curve and desire to be in the middle instead of behaving like any other particle we'd expect. So let's set up a little experiment. We do the same experiment we did before, where we shine the light at the two slits and where we got the interference pattern. But this time we have little photodetectors, these little things that basically check which slit the photon goes through on each slit. So we can just see which one it's going through and understand what the heck is causing it to behave like that when it looks like a particle. And so let's just run the same thing again, but we check which it goes through. What do you think the pattern is going to look like? Oh, what? Why does putting the detectors there just to know which slit it's going through cause the wave-like behavior to stop and cause it to act like a particle? What's going on? Oh, it's a wave until we look at it and it gets shy? I don't know. What's going on? Wait a minute. Earlier here we saw that it only looked like a particle when it was detected, when we tried to find a specific one. Are are we changing the outcome by observing it? Yep, that's exactly what's happening. By adding the detectors to try and find out which slit the photon goes through, the light stops acting like a wave and starts acting like a particle. And then, which indicates that light is a wave until it is observed. And so, by trying to observe it here, it acts like a particle at the slit and therefore moves like a particle through them. But when we allow it to, when we don't have those detectors there, we get the interference pattern back. And we can see individual photons in this interference pattern, but then they only start acting like particles when they hit the detector. And this is probably one of, if not the most important ideas in quantum mechanics. It's actually the same idea behind Schrodinger's cat, except in Schrodinger's case, he used an atom that would decay into another atom by radioactive decay. But it's the same idea, and it's what we call a wave function. A wave function is basically how we describe the behavior of a particle when it's acting like a wave. And it describes the probability of finding a particle in a certain state or in a certain place, and takes all of those probabilities and turns that into a graph. And when we observe when we observe what's going on with a particle, the wave function collapses. And the point of the Schrodinger's cat experiment was to show that this is really weird, because we're basically describing particles, like individual particles, being in multiple locations, multiple states at once. And when we try to apply that logic to a cat in a box, it causes, like, the particle is both decayed and not decayed. The photon is both particle and wave, yet these are seemingly mutually contradictory states. And when we apply them to something like a cat, it's alive and dead. And so that indicates that the way quantum behavior is far, far removed from anything we experience at our scale. It's fundamentally different and unintuitive. And it's part of why quantum mechanics gets wild. And so, but in the end, what did we learn? Well, we learned that light behaves like a particle and a wave. It's both. And whether it behaves like a particle or a wave is completely dependent on how you observe it and where you observe it. And ultimately, this is an indicator that for subatomic particles, for electrons, for photons, for basically anything on that scale, the way they are is very different than what might come naturally to us. And we use tools like math and science to be able to explain them, even though they're not intuitive to us naturally. And so, yeah, mine was a bit shorter, but I'd say, do we have any questions?
But just because this stuff tends to be probabilistic and very, very complex to understand, one way I've tried to assess situations like this for myself is by the belief that once we start getting to interacting with fundamental particles, the only way you can measure them is by having them interact with other particles, which could end up changing them. Is that generally a proper assessment of what's going on here, that we cannot observe or measure quantum particles without fundamentally changing them, because the only way we can measure them is by interacting with them?
That is exactly true.
All right.
That is, yep, that's completely that's the complete that's yeah, that's completely right. And that means that we have to have a different model to understand how things behave when they aren't interacting with something. And that's what the wave function does. The wave function gives us a way to express how these things are behaving before they interact with something.
Interesting. Thank you, Cave.
And, and so, and guess what happened? Guess what applies to a lot of quantum mechanics is, as was being discussed earlier, statistics. It's all probability all the way down. Turns out God does play dice with the universe, and Einstein was wrong. But yeah. And so I kind of wanted to be able to give kind of an introduction into what kinds of ideas we work with when we start learning quantum mechanics. Light waves are shy then? Doesn't it work if we
Well,
see it?
I do have to say, you say that like, well, Einstein is wrong and God plays dice with the universe, but the thing is, he only does it at quantum scales, and we still don't know how the fuck to reconcile physics at the macro scale with quantum mechanics.
Yeah, quantum mechanics is basically
we have like two completely different models for these things, and we don't know how they work together.
Yeah. Good old grand unified theory. The scientists, the physicists' copium.
Yeah, like we were talking about earlier together in the chat, the more we know, the more we realize we don't know anything.
Mm-hmm. Yeah, and in quantum mechanics, there's crazy things like there are fundamental limits to what can be known, because that's stuff like the uncertainty principle, which is also cool and I could ramble on about. But yeah, the study of God does play dice with the universe. The study of quantum mechanics is figuring out how he weighted them.
Wow.
But yeah.
Well, yeah, that was definitely a presentation. I have to say that my brain was exploding with each slide. Each slide was a brain explosion for me.
So yeah, I remember when I was first learning this, it was like, yeah, I was having that exact reaction. I was like, what? Wait, what? Ugh.
Quantum physics are an info hazard.
Basically, it's kind of like being exposed to an eldritch horror where like your brain is not fundamentally built to understand the universe this way, but instead of like going insane, you just get a degree. Well, you do go kind of insane.